Now we consider the next model. This time we consider channel coding. Coding for channel with states, it's a so-called Gelfand-Pinsker problem. So we look at the situation when a source sends a message W to encoder. And the encoder wants to send this to a receiver by mapping it to a sequence xn. This looks like a discrete membrane channel. But the difference is that the channel has interference here by this discrete membrane source PS. This is called a state of the channel. So depending on the letter here, we have different probabilities here. So we look at this problem in a non-causal fashion. That means the encoder receives W and all states for the whole block length he receives Sn. And then he, depending on W and Sn, he creates his sequence Xn and sends it over the channel. However, the decoder do not have any access to the state sequence. And here I have to make an estimate of the message W hat. And we want to have the error probability arbitrarily small if the block length goes to infinity. Now you can ask, how realistic is this model? Of course, we can also consider this model in a causal fashion. That means the state sequence, the sequence S, is sent to the encoder after every symbol he sent. So if he sent a symbol, he gets a new state. And then you can think about perhaps the encoder always makes some channel tomography, receives this, and then encodes the next symbol. But is also the non-causal fashion, is it also realistic? Yes, it is. So for example, you can regard the encoder as an encoder of a broadcast channel with two receivers. Then the two messages W1 and W2 for the receivers might be mapped to sequences as 1 to the n and as 2 to the n. And as 1 to the n can be thought as being interference for as 2 to the n. Furthermore, the encoder does have non-causal knowledge of W and therefore of S1 to the n. So it's exactly this model here. There's a second example. So now we suppose we are given a memory device that has been imprinted, such as a compact disk. Now we wish to encode new data on this old disk in order to reuse it. And we can read the data as n already in the memory. So we can view Sn as interference that we know non-causal. And now further, we wish to model the effect of errors and that an imprinting device can make during imprinting by using a probabilistic channel. And again, we have exactly this model here. So these are two examples that this model is also realistic. Let's look at the FDG of this problem. Here you see that, so we look at block length 3 again. So you see the sequence x1, x2, and x3 depends on W, but each symbol depends also on S1, S2, and S3. That's what the encoder did. Now look at the receiver. The receiver received now Y1, Y2, and Y3. And of course, this depends on X3 and S3. Depends on X2 and S2. Depends on X1 and S1. If he also allows that he can randomize, then it could be also depend on an external random variable. But we will not use this in the first proof. And depending on Y1, Y2, and Y3, we make an estimate of W hat. Now I will give you the result before I come to the analysis. So if you look at the result, we get the following theorem. So the rate is equal to the maximum over all PUS, so channels from S and U, such that the mutual information between U and Y minus the mutual information between U and S maximize, where U as X and Y forms the Markov chain. And then RGP is the capacity of the Gelfand Pinsker problem. You immediately see that we need, like in the previous model, again, somehow the helping variable, because it comes in here in the formula.